instructions. So program control instructions. Once again, the lecture we're looking at principle-wise applies the same as if you were doing the software, but in terms of the syntax and the the way the instructions look, that might be different because the lecture material uses a little bit of an outdated version of the software. So just be mindful of that. There's a little bit of a transition between what we talk and what you're gonna see. So there is a number of what's called program control instructions. And these are special software instructions within the PLC programming environment that are good ways to safeguard the quality assurance of a ladder logic project. And so we're going to be talking about this program control instructions today. So here's a diagram that has one of them, actually two of them, the JMP, which stands for jump, and then the label. Those two instructions are similar, but not the same. And we'll discuss some of them today. All right, so let's look at the usage of program control instructions. They're used to disable a segment of a logic program or to move execution of a program from one place to another place. That's the main use of program control instructions. In the older software, they look like this, right? We have an Allen Bradley manual SLIC 500 and MicroLogic 5000 program control instruction group. And as I guess, there's actually exactly 7 program control instructions: jump, label, jump subroutine, return, subroutine, terminate, master control reset, and suspend. So those are the 7 most popular program control instructions. We're going to see them here one by one. Okay. So let's look at the reset instruction. I'm sorry that the fonts are a little bit overlapped. And I guess that's why the reason is the layout here. Something is not working right. So there is a hardwire master control relay. Okay, and they're used in relay control circuitry. They're actually used to provide input and outputs so that you can shut down an entire circuit. As you can see on this ladder, or actually a schematic diagram, we have 2 MCRs, right? Master control reset instructions. And in this case, they're actually hardwired. It means they depend on this giant motor starter. And the idea here is that if those MCRs are not engaged, nothing else is going to matter, right? Only the first rung is going to semi-work, but nothing else is going to matter. So there is a master control relay instruction, hardware based, right? It's called MCR, and in the software world, it clears all set non-retentive output rungs between the pair MCR instructions. The program MCR is not a substitute for the hardware MCR instruction. So it's always recommended that all PLCs will include an MCR and emergency stop switches to provide safety and effective shutdown of the I/O power. So master control reset instruction is the master of all instructions. Here is a program master control reset instruction. You can see it right here. It's at the beginning of the whole thing. There's the MCR. If that MCR is not engaged, right, nothing else is going to happen. And so that's what the MCR does. right? And there's a little note here that when the MCR is de-energized, all non-retentive outputs will be de-energized. But when the MCR is de-energized, all retentive outputs remain in the lit state. So there is the building of the MCR. Notice also that the MCR needs a pair. And so what it is you have to block typically all the program with a pair or a set of MCRs. So MCR is at the beginning, MCR is at the end, okay? And so that's how the MCR syntax goes. All right, simulated master control sensor and unable to do that. So I was afraid this was gonna happen. I am gonna, if you guys have patience with me, let me actually exit out here. We're gonna miss the simulations. And what we're gonna do is I'm going to download the actual I'm gonna close this out. The download's always high for some reason. So let me see if I can pull up a reel. Sorry about that, guys. But I think it's better that we pull up the real one. Now, where are my downloads? Oh, there you go. So here is my download. I'm gonna open up the original PowerPoint so you guys can see the animations. Okay, it's probably gonna be better. Here's where we were. So let me play this out. And there's the master control reset. MCR is active. That means anything else can be right on or executed. Pilot light 1, solenoid 2, which is enabled by 2 different limit switches. And everything stays as it was when the master control reset instruction goes off. Okay, so that is the master control. There's also the MCR fan zone with the zone true. And here's an example of how that would look. And this idea of the fan zone is what I was talking early on, what I said that you need a pair. So you're zoning the whole program to be obedient or submitted to the MCR. So again, we have MCR at the beginning, MCR at the end. We have input B, output A. We have a timer on tone, right? We have a few other inputs, the latches and unlatches. Have we talked about that latches and unlatches, guys? I don't know if we talked about latch and unlatch yet, but the basic idea with the latch and unlatch is that you eliminate a couple of IOs when you use the latch and unlatch. The latch obeys to basically a pulse trigger that when present, it latches, and the latch instruction has its pair or partner, which is the unlatch. And so they both have the same address or label, if you will. And what you need is a trigger to latch and a trigger to unlatch. And you're eliminating other accessories that you actually normally use to latch a circuit with the latch and unlatch instruction. All right, fans zone with zone false. Here again, we have an MCR where the fans start. an MCR with the fence ends. And it's essentially the same idea here, except that it says with the zone false. That means when anything goes false, then the MCR would be enabled and enter in. So here is a simulated scenario of the MCR active. Okay. We have a non-delay timer. This is a non-retentive timer. All right, there's other uses to this idea of the MCR, fellows, in addition to controlling power for an entire system, and that system can be sectionalized. MCRs are also used when only a portion of a program is required to be isolated. For example, inhibit zones of the program while loading recipes, monitoring emergency stops, establishing preconditions to synchronize a machine on startup. So this is in addition to what we already seen, other ways that the master control reset instruction can be used. All right, let's leave the MCR behind and talk about the jump instruction. JMP is used to jump over certain program instructions when certain conditions exist. The label instruction is used to identify the ladder that is the target destination, but does not contribute to long continuity. So that's the label instruction along with the jump instruction. All right, JMP operation program. In this case, when the switch is turned on, there's going to be a jump to Q20, and there's actually a label companion, label Q20. In conjunction with the jump instruction. So observe that when input 1 is engaged, jump instruction is engaged, and then there's a jump that goes over directly to the label instruction. All right, here's a larger ladder program. Effect on instructions of jump rungs. You're going to have a situation here where timers should be programmed outside the jump instruction because they could be frozen. And so here's an example of a on-delay timer, which is actually outside of the jump instruction. And then on rung number 4, we have the instruction itself. Jump program runs are not scanned by the processor. Input conditions are not examined, and output remain in their last state. So there we have a jump instruction that it's going to jump over instruction 5, 6, and 7 and go directly to rung 8, right? So at the moment that LLS1 engaged, the jump instruction is engaged, which is going to take the program over to rung number 8, and it's going to skip all of that. What's the purpose of jump instructions, you may ask? Well, if you have a certain multitask ladder project and the conditions are so that you don't have to run the first 10 rungs, then you can have a jump instruction that will go to run 11 and run 11 through 15 instead, right? Because otherwise that will be, time consumed, checking instructions 1 through 10 without having the need to do that and being able to just directly jump over instruction 11. So jump is jump. That's the idea of it. Jump to label from 2 locations. You actually can have the jump instruction, and you can have it to jump from various locations. In this case, input A and input D are the triggers for jump instruction. It means that either trigger or input A or D, will trigger the jump instruction that will move or take over the label instruction, right? And so you could have the same jump instructions in multiple rungs enabled by different triggers. That's the case. All right, so MCR and jump are behind. Let's look at subroutines. All right, and a subroutine actually is a short program that is used by the main program to perform a specific function. There are three elements that are associated with subroutines. You can have the JSR, jump to subroutine. You're going to jump to a designated subroutine instruction. You can have RET, return from subroutine. It's going to exit the current subroutine and returns to previous condition. And then you could have SBR, which is a subroutine that identifies the subroutine program. So those are subroutines, very similar to jump, but a subroutine is a short program that is used within the larger main program. When a subroutine is called from the main program, the program is able to escape from the main program and go to a program subroutine to perform certain functions and then return to the main program. This subroutine thing actually works in conjunction with the jump instruction. You can see that. Jump to subroutine instruction, and then jumps, and then there is the unconditional return, which is going to bring back the program to where it actually jump over to the subroutine. So that is the subroutine. It redirects logic execution from the current ladder file to the specific subroutine file. And jump to subroutine SBR file number U column 3, and then goes to the subroutine and then returns to whatever was that takeoff from to go to the subroutine. There's a flashing pilot light subroutine program. Anytime the weight on the conveyor exceeds a preset value, the subroutine program is going to be scanned and the pilot light changes from on to flashing. So that's what this specific subroutine is going to do. Here is the actual ladder program. There's the main program. And along the line, there's going to be a subroutine program that will monitor a timer, actually two timers, T40 that will feed T401, and that it's going to be triggered by the jump to subroutine U3 if the sensor senses that the weight exceeds the required weight on that conveyor system. There you go. System running. At some point, the sensor is going to come on and it's going to take the project to the subroutine and execute it. There you go. That is. So you have a timer that is actually flashing back and forth the light, the pilot light. Here again, we have a subroutine, setting up a subroutine file. And again, this is going to be a little bit different, guys. When you do it, if you do it, I'm not sure that we're going to be doing subroutines, but it'll be a little bit different than what appears here. The concept is the same, but it'll be different. So subroutines can be nested, just like timers and counters can be nested or cascaded. You can nest or cascade subroutines. You can see here that we have a main file program 2 that has a subroutine 3, right? And that's level 1 file 3. Under that subroutine, there's another subroutine, level 2 file 4. And under that subroutine, there's another subroutine, level 3 file 5. So subroutines can be built in or cascaded in or nested in if there's a need to do that, right? And so that's the more complex the ladder program, the more need for nested subroutines you might have. It's a good practice. All right, we're leaving MCRs, jump instructions, and subroutines and such. And then we're looking to another control type. It's called the immediate input, immediate output instructions. Another instruction that allows you to update data prior to a normal input scan. So you can update data prior to normal input scan. Okay, so you're gonna have inputs being read, and then inputs being written on the IO data file. Then you're gonna have an immediate output, input, and then you're gonna have a program logic scan. And that's the IIM. That's part of the, it's not in the group of the control, but more or less in the IO instruction. So when the run is true, whatever makes this run true, the program scan will be interrupted and data from a specific input slot will be transferred to the mask to the input data file. So the concept of masking, right? It's basically you're gonna test out, and the mask is a given value, right? For instance, if you want the output of this instruction to be true, only when all the inputs are true, you're gonna have to mask this with an AND function, right? And so masking, it verifies. It verifies. So when the run is true, the program scan is interrupted, and here is what happens, right? With that mask instruction. The length is 2, right? And is 2 because it uses two words, right? So 2 16-bit words, right? So the first hex represents a byte. The second hex represents a second byte. So that's 16. Right? The third one represents a third byte. The fourth one represents the fourth byte. So that is actually 16 times 4, which is 232 words, right? All right, control logics have no immediate input instruction as they use asynchronous IO control. So control logic is another software technology that we used to have or have in some legacy programs to be able to do this idea of the immediate control. So we're not gonna be too worried about that using a new software. Another important and dangerous instruction, I will say, is the forcing external IO address. This is actually very powerful. I've used it on the field, and it's a powerful instruction, but also a dangerous one, right? It's actually used for various purposes. One of the purposes of the forcing IO instruction is to troubleshoot systems. You can troubleshoot systems, all right? The other purpose is to do emergency stops, right? And so these forcing instructions are very powerful, but they're very dangerous too, right? Forcing allows the PLC user to turn an external input or output on or off from the keyboard of the programming device. So you really can mess things up. I think about cyber attacks on industrial controls. This could be one of those, right? A cyber hacker that will take over your system and that will force either your inputs or your outputs to run or to stop. All right, that'll be awful. Okay, forcing is accomplished regardless of the actual state of the field device. So it doesn't matter what the response of the field device is. If you can take over the IO table and force on to do that input or output, whatever you want to do, it should obey. It shall obey to you. Okay, so again, this is a powerful but also dangerous type of instruction. And here on the input table, you're going to see a 1 when the instruction is forced. On the output, you're going to see a 1 when the instruction is forced. In this particular case, whatever is connected to bit location 3 and the input is going to be forced to be on the controller. And in this case, whatever is connected to the 0 output or rung 2 is going to be forced to be on no matter what's happening. All right, forcing an input on. We've already seen how that is. This particular input has a force on it. All right, so it's forced to do whatever you the user wants to do. Here it is. Here is normal operation. Now the user is going to go into the IO table. It's going to double click there and type a 1. You could also step on the ladder program, right click and enable forces, just like we're doing here. So that's how you can force that instruction. And you could use this instruction ethically to troubleshoot systems or to do emergency operations, right? That is the purpose of the forcing instruction. You could also force an output. Here is a force on an output. In other words, it doesn't matter the condition of the program or what's happening outside. If you force this on, it should respond. Now, here's a question for you in the audience. What happens in this case if I force on output to 5, but the actual output doesn't respond? What do you think is probably happening? Any opinion, guys? What do you think is happening? I am forcing on from my programming device, but the device is not responding. And that force on could be to turn it on and to turn it off. But let's just say that the system is off and I want to turn it on by force, but the system doesn't run. What do you think is the problem? Here's how you force the output on. Similar to the input force on. There we go. Forcing the output on. It is the same idea, right? You're gonna step into the table and force that instruction to do whatever you want. Uh-oh. Sounds like our PowerPoint is not responding. Yeah, it collapsed it. All right, we're gonna restore this and go back to where we were. Close that. We already discussed that. So routines, we talked about that already. We talked about that. We are talking about the forcing on and off, using the programming device to force on. And this was the last one we saw. By forcing outputs off, you can prevent the control from energizing the output, even though the ladder logic which normally controls them, may be true. Okay. You can enter and enable or disable forces while you're monitoring your file offline or in any process mode while monitoring your file online. In other words, this forcing can be done while you're running or not running your project. And here's the part that I wanted to stress for you guys. If you ever come across being the manager or overseers or plant engineer, if used incorrectly, force functions can cause disasters, right? Injuries to persons working on a system, equipment damage. You must understand the potential effect that forcing given inputs or outputs will have on machine operation in order to avoid possible personal injury and equipment damage. It's a very powerful, but also dangerous form of program control instructions, right? The force instruction. You've already seen some of that, and it can be disastrous. Safety circuit is the last part we're covering. We're doing pretty good with our time. Actually, we're gonna end early today. Sufficient emergency circuit must be provided to stop either partially or totally the operation of the controller or the control machine or process. The circuit should be hardwired outside the controller for safety. And here's the safety wiring requirement for a PLC installation. Okay, you have your PLC modules, and notice that we have an MCR here. And there's also the emergency over travel limit switches and all the rest of the stuff that is required. The master control relay must be able to inhibit all machine motion by removing power to the machine I/O devices when the relay is de-energized. We already discussed the MCR, right? And that's another very safe way to put that. Now, there's also safety PLCs modules available for applications that require more advanced safety functionality. And here is a Rockwell automation safety module. It's got a lot of things, 12 basic module status, alphanumeric display, node address switches, baud rate switches, USB port, device net communication, terminal connectors, input status indicator, output status, IP address display, Ethernet connectors, service switches. You can add on safety modules. Both standard and safety PLCs have the ability to perform control functions, but a standard PLC was not initially designed to be fault tolerant and fail safe. Safety PLC have redundant or dual microprocessor. Many times, safety PLC will have internal output circuits associated with each input for the purpose of testing the input circuitry. Safety PLC use power supply designed specifically for use in safety control systems and redundant backplane circuitry between the controller and the I/O modules. So that's safety modules. The use of field generator starter auxiliary contact is safer because it provides positive feedback to the process about the exact status of the motor. So these MCR systems are usually recommended. All stop buttons should be wired using a normally closed contact program to examine for on and off conditions. You guys tried it a little bit, and that's the idea, right? Stop is normally closed, start is normally open. Using normally open contact program to examine for and off condition of precision logic, but it's not considered to be a safe, right? So you want to be safe as you do that wiring. All right, the last one is selectable time interrupt. I'm not sure that we have this on the CCW software. We're going to go rather quick here. Okay, and the other one is the fault subroutine file. That's another to determine how the process responds to a programming error. You can modify that. When the process detects a major fault, it looks for a fault routine. You're usually going to have a fault mode on your controller. When there's a fault routine and the fault is recoverable, the fault routine is executed. If the fault is not recoverable, the fault routine is scanned once and shut down. You might have seen when you're doing this, it's almost like overriding that fault. If you've had a chance, usually happen with hardware. When you're trying to download something to hardware that is faulted, it gives you a caution and it says you want to write this and override the fault, or you want to log or inspect that fault. All right, temporary end instruction is used progressively to debug a program or conditionally omit the followings of your current program file as a routine. When the run conditions are true, the instruction will stop the program scan, update the IO, and resume scanning at run 0 of the main program. So the TND instruction let your program run only up to this instruction, right? And actually, it's a very powerful testing and diagnostic instruction. You can move it progressively through your program as you debug each section. So you can program the TND instruction unconditionally or conditionally according to your debugging needs. Okay, so it's actually a good debugging tool, right? You basically segmentize your program to test whether your program is responding sort of line by line, right? Without having to be guessing where the problem might be. Here's a temporary end instruction. It's at run number 3. Okay, so run 0 through 2 works fine. As you override the terminate instruction, you can test the whole program. Right, but that's how that works. It's a diagnostic tool. Suspend is the last one, I think. Yeah. To identify conditions that are disruption and prevent debugging. All right. When the run is true, the suspend output places the controller in the suspend mode, and the PLC immediately terminates scan. There's a way to suspend, right? All ladder logic outputs are de-energized, other status file have data present when the suspend instruction is executed. The SUS, almost as either, right? Instruction writes the suspend ID number to S7, which is the memory location, as it executes. You can include several SUS instruction in a program, each with different suspend ID.